Now you want to take away the negative. Just circle the negatives and put an arrow.
All right, guys. Guys, let's take a look at this. I gotta tell you real quick. Guys, can somebody tell me? What seems to be my favorite, guys, my favorite kind of question when I say a student does something, blah, blah, blah. What, does anyone know what my favorite kind of problem that is? I've given you many of them. What happens in the problem? The student made a mistake. All right. One of the most fascinating things about being a math teacher, I know you guys are going to teach other subjects, so that's going to be more fascinating for you, is when a student makes a mistake, it is really important to understand what mistake they made. Because then you can build, if they just made one little tiny thing and they almost got the idea, or maybe they made a mistake in such a way that it would work sometimes, but not in that case. I don't even know if you guys are with me. One of the most fascinating things about teaching in general is just all the different mistakes students can make and why they thought it was okay. So that's going to be true. So, if a student did believe this was true, what mistake did they make? They just took 15 and 20 and combined them, right? And they took 40 and 110 and combined them, correct? Yes? Yes? Okay. That wasn't what I asked. You guys might not even have seen that, but I could have reworded it to say that. Yes? Now, real quick. For example, what is 10% of 50? Anybody know? 10% of 50. What is 10% of anything?
It's 5.
Yeah. 10% of anything is 1/10 of that thing. So 10% of 50 is 5, right? So 10% of 50 plus 10% of 50, is that 20% of 100? That doesn't make any damn sense. No. 10% of 50 plus 10% of 50 is 20% of 50. Maybe? What's up? Yes? Yeah. So if I take a piece of 50 and add it to another piece of 50, I get a slightly larger piece of 50, yes? Right. Okay. So this is not even kind of like terms in a way. No. They don't have the same base amount. So of course I think most of you guys probably just did the work, right?
Yeah.
What'd you get here?
15 times 40, and you get 6.
6.
And then you did 0.20 times 110, and you get 22.
22.
And then you add it, and then you get 28. And then what I did for that one, I got 0.35 times 150, and it gets 52.5. But it does not go into that, so it's a big no.
Okay. I like it.
Can you do number 2? I'm kind of lost on that one.
All right, guys.
I mean 2. I said 22.
Everybody.
Nope, we're losing our minds. Yep.
No, you guys have lost your minds. Everybody. Hello. Hi. Hey. Now. Okay, I love you guys. Even you guys. Okay. This one. What do you guys remember? If I put a dress on sale, if I put something on sale for some percent off. So like if I take 20% off of a price, what percent of the price is still there? 80. So if I have a dress that's off 65% off, what percent of the price is still there? 35. So 35% of what it was is what it now is. Yes?
No.
Okay, let me try this.
Too many words in that sentence.
So I have something, it's cost some amount. Okay, we don't know what that is. If I take 20% of this away, yes?
Yes.
If I take 20% of it away, won't that now equal the sale price?
Yes.
Yes?
Yes.
Guys, please. Okay. If I take 20% off, what's left is the sale price. Is everybody with me?
Yes.
Okay, that's cool, right? Okay. So, what is left here? What percentage is left?
80.
80% of what?
X.
X. And that would equal the sale price. I like it. Okay, now, coming back. So what I can always do, for example, if I had 10% off and the sale price is 30 bucks. Right, let's just say I got that. 10% off of something, I don't care what it is, and the sale price is now 30 bucks. 10% off means the 30 bucks must represent what percent of the original? 90%. If I take 10% off, there must be 90% of the price left. And that is 30 bucks. They tell me what the price is that's left at the end, right? So that means the 90% that's left must equal $30. And then I just have to divide to get the answer, correct? Yeah. Okay, so let's look at this one. What do you got? 65% off. So what percentage of the unknown original price is left? If I take 65% off, what percentage is left? 35%. And that is equal to what?
168.
We know it's got to be 168. The amount that's left, which is the price they're going to sell it to me for, must equal the percentage that was left after they took some stuff off. And how do I solve this?
Dividing, and you get 480.
480?
I didn't get that.
Yep.
Well, let's see. Alright. We got this great one. I liked it so much. I'm down it twice. Poor Joe's like, just make me pay for the damn mortgage once, Jeff. So Joe's yearly salary is $48,000. He's if he's here, he's having a rough time. 16% of that, he allows 16% for the mortgage. Now this, guys, I keep losing you. Stay with me. Do you guys see how this one's a very direct? There's no weird shit. There's no like, what's the after effect? No, this is direct. He's got an amount of money, and he put a percentage of that money for something. So here you just got to do what?
You gotta do
45,000 times 0.16.
Yeah, 16% of 45,000, which gives you.
Oh, and
7,200, and you
7,200.
divide that by 12 because it's 12 months in a year.
Yeah, there you go. Yearly salary.
And it equals to 600.
What's
When
that?
you divide it by 12, you get 600.
Yeah. Okay. All right. Now that one I could. Yes.
Wouldn't you want to divide 4,500 by 12 to see how much he makes per month, to make sure he has enough to pay it off? Because it says what amount can he afford to pay per month? Well,
I'm not sure what you're saying. He's guaranteed to make enough money because he's only putting 16% of it towards that.
I don't know. I just
No, I understand what you're thinking, but he's only putting 16% of it. So by definition, he's got enough money. Now the real question is, will 16% of that cover something anywhere, right? Maybe, sure, definitely not here. Okay. Then we got some people's favorite problem. Ruth sold her entertainment system, made a profit of $3,800. So they tell me the profit of $3,800, different tense, but it still is 20% of something. And then they ask you for that something. So I kind of appreciate some of you guys are worried about, do I have to add some more shit to it or whatever? But it's a direct relationship. Once I do it, I get the answer. Andrea, do you have a?
I got 30.
How'd you set it up?
I set it up 3,800 divided by 0.20.
No.
Well, sorry, 3,080. I'm sorry, 3,800. Equals to 0.20x.
Okay.
And then you divided it.
Okay.
And then I got 19,000.
Sweet.
And you had,
This for forget the zero, or unless you wanna add it just for calculations, that'll work too.
Oh, the 0.20?
Yeah, the 0.20, that's what I'm trying to say.
We know we don't need that zero. Poor little zero. Okay, this one also freaked a few people out, but please, what's that symbol by itself mean?
Negative.
Okay, be more technical. You're like, negative? What is this? Negative. So, what's the mathematical term?
Minus.
When you have two negatives, the opposite will be a positive.
It's the additive inverse. Okay, I like it. So another way to say it that's not really quite acceptable is it's the opposite, right?
Yeah.
So if A is negative, negative A is
Positive.
positive. Come on now, you can give me a negative number.
-2.
All right, what's negative -2?
Positive
So you
2.
can ask. We know A is negative, therefore this is positive. We know B is negative, therefore this is positive.
Positive
When
B.
I add two positives, I get positive.
You get it?
So is it negative?
No.
No. So that's the thing where I ask my students, what's this? Is this positive or negative? And you can imagine most of them say negative. Some of them just don't say a damn thing. You're just waiting for it. I'm going to wait till you say something, John. But how do I determine if that's negative or positive? Why is that not negative necessarily?
You don't know what it
I don't know what the freak X is. If X is negative, that is positive. If X is positive, that is negative. And of course, if X is 0, it's neither. Okay. So this one, hopefully, see if you guys remember. What's the additive inverse of 3/7? We just talked about it. Yeah, negative 3/7. It's awesome. Whatever the thing is, you stick a negative sign in front of it, or change its sign. And what's the multiplicative inverse? Yeah, because that's also known as the
Reciprocal.
reciprocal. Okay, I love you guys. Some of you guys think you're in a game show. I love it. Now, who thinks they got this one right here? All right, I know a few of you got it right.
I'm not sure if I got it right, but I did it with
Where
someone.
should you start? Where should you always start?
The parentheses.
The innermost, right?
Yep, and then the negative plus times a negative would be a positive, so it would be positive 8y, and then a
All right,
negative
all right,
and a
all right.
negative
Wait,
would
wait,
be
wait.
positive.
Let me catch up to you. Everybody! So guys, right here. And this is where, Emma, you can do this thing.
That would be a positive y.
I like it. And now,
Wait, negative 8.
of course it's negative 8.
Oh.
So I'm not doing anything with this thing yet, am I?
No.
In here, there was a minus next to a minus that makes a plus. Now what happens with this?
A negative and a negative would be a positive 8. And a negative and a negative would be a,
Wait. So minus and negative is plus,
yeah, plus,
and minus and positive is minus.
minus.
Yes?
Yeah, we got it.
Guys, is there a number here? Is there a number here?
No.
Is there a number that we understand is here?
1.
1. So isn't this -1 times this, -1 times that distribution? So negative sign distributes like anything else because it's an understood -1. So whenever you have a negative in front of any parentheses, all the signs inside change because that's what minus times that stuff does. Yes? Okay. All right. And then finally, I'm kind of hoping you guys.
Can I draw that one on the whiteboard? Wait, like that.
Sure. Go ahead.
Thanks.
Do I have other? Let me give you better visual aids here. Hold on.
So,
Slow your roll there. Here. There's.
pretend this is a garbage chute.
Oh.
That's how I explained it.
Well, I had help. So, we have then we have 3 negatives. But we both know that's not going to be enough. So we added 3 more positives to get 5 positives, and we throw these away. And therefore, we will have 1, 2, 3, 4, 5, 6, 7, 8, but with these gone, that'll be 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8.
Okay.
And that.
So I like what you said. You gotta be a little careful. So we start with 5. We got 5, definitely. And then and again, you're thinking from the student's perspective.
I just added the garbage chute.
Before we've talked about negative times negative is positive, they know subtraction means take this away. They draw 5 positives. I don't have a damn single negative to take away. How am I going to take 3 of them away? So this is where you introduce a 0 equivalent. I just added 0, right? That's what Andrea did.
Mm-hmm.
I just added 0, so I've not changed. It still represents 5, because all this stuff just goes away. But now I can do that. Now I can actually take 3. I can do physically take 3 away. And that's still keeping the idea of subtraction there, right? They still have a visual. It's still a manipulative thing they can do. So I'm not changing the definition of subtraction. It has to be the same definition. It will lead to a shortcut of making this a freaking plus, but we're not there yet, right? So then I can actually, like Andrea said, take this away, throw it in the garbage can. I think I gotta throw the garbage can in the garbage can. And then I can just count what I got left. These are gone. And then I got 8 positive. Bam, bam. All right, I love it.
Bam, bam.
Bam, bam. All right. Now, any questions from all those?
What would it be, since this is going to be based off of the quiz? Is this exactly the practice quiz, or is this the same idea?
Like I said, it's sort of like a practice quiz. I don't normally do practice quizzes, but again, I'm just trying to be nice, see what it feels like. All right, so rest of the time we're going to discuss, so again, 9-1 is extra credit. Cool, right? If you do it, it'll add into your homework grade. So if you actually have 100 homework grade, you'll have an over 100 homework grade if you do the extra credit too. Whoa! Okay.
What if I got an 85? What happens if I have an 85 and I do the extra credit?
Then it will be a little more than 85.
Like, per se what? Like how much is the extra credit on average?
So guys, when I do extra credit homework, if you have a homework that's missing and you do the extra credit homework, it just takes that guy's place.
Oh.
So if you don't have any homework missing, then it's extra. So it's going to be over 100 in that case, yeah. All right. So what we're getting into is some exceptionally weird shit. What I want to do is, I think I told you guys there was a video, I'm going to show it to you today, hopefully, we'll see, where they discuss complex numbers, imaginary numbers a little bit. Oh yeah. That's not the main focus of this video though, but there's some other cool shit around it. So, what we're getting into is, for example, can somebody tell me rational numbers? Remember, that's just another name for fractions. What kind of decimals become rational numbers? You guys remember, what has to be true about a decimal for me to be able to write it as a fraction? Give me an example decimal that I can write as a fraction. Very simple. Just give me a decimal.
0.5.
0.5. There we go. Now we're getting somewhere. So as long as it stops somewhere, yes? Woo! So even if it stops way, that's a 3. Pretend like it's a 3. Blah, blah, blah. I can still count tenths, hundredths, thousands, or I can just count and put that many zeros after one on the bottom. Are you guys with me? So if it stops, it fits into a place all day. Does that mean if it doesn't stop, it can't be a fraction? We know that's not true, because what's 1/3?
0.3.
Yeah, 0.3333 forever, yes? So, if it stops, it's immediately a fraction, an obvious fraction. If it's got a pattern to it, a repetitive pattern like this, then it's got to be strictly repeating. Then I can figure out a way to write it. And actually, I showed it to you, and there were some problems, I think, in the homework, if I remember correctly. I had to make repeating decimal into a fraction? Okay. Are all decimals terminating or repeating?
Yes?
No.
What?
Terminating?
Do all decimals stop? That's terminating. Or if they don't stop, do all decimals have a pattern, have a repeating thing to them?
No.
Does anyone know any
Pi.
famous ones? Famous
Pi.
pi. There you go. Pi is a good one, right? As far as we know, it has no repetition, and we've taken it out to the stupid amount of places. Do you guys know that people memorize places of pi? I'm like, no.
Well, there was this one kid who remembered pi and never remembered a movie Pi.
There you go. Okay. So, one of the first, this is kind of a true thing about history. They tried to figure out if something squared is 2. Something times itself, could it be 2? Right? And let's make this even more general. Let me make this just a number. And let's make this into a very explicit rational number. Is there a fractional number that I can square and get 2? No. And in fact, if I sort of try to explore this a little bit. Okay. So here's the weird thing about, I don't want to say this. If I take a square, a perfect square, it's going to have, how many prime factors do you think it's got to have? Or not how many, but is there anything special about the prime factorization of square numbers? Can a square number have like 1 3 in it? Think about this for a minute. Can a squared number have 1 3 in it? You can do it. No, right? So what I'm trying to say is, if I have a square number, 1, 4, 9, 16, 25, so forth, is it possible to factor any of them and have a single number show up? No. They always have to show up in pairs, of course. That kind of is the whole idea of squaring stuff. Yes? You guys with me? Maybe? Okay. So generally, if I had some square number, and I just take A, it already has prime factorization. When I square it, it's going to have 2 of these and 2 of these. And whatever it's got, whatever A has, A squared is going to have 2 of all those. It's freaking impossible for a square number to have one thing. It's got to have to show up in pairs, which means it's always got to have an even number of prime factors. You guys kind of with me now? Since they got to show up in pairs, it's got to be an even number. So A squared, how many factors does it have? I don't know how many, but I know it's an even number. Yes? B squared, is it a square number? Yes. How many factors does this have? Does this have? How many factors does it have to have? I don't know, but it's got to have an even number. Yes? Okay. So if this has an even number of factors, how many factors does this have? Because there's a 2. It picked up another factor, didn't it? 2b squared. B squared has an even number. 2 is another one. That makes it odd. All right, so this is a very strange little proof as to why there is no fraction squared is 2. This is kind of a weird way to look at it, but this has an even number of factors. This whole thing has an odd number of factors. So could they be equal to each other? Hell no. Yes? Okay, maybe. So we all know that the square root of 2 is not nice. Yes? So that's one way to put it. The square root of 2, I can't write it as a fraction. The square root of 2 is a non-terminating, non-repeating decimal. 1.414, blah, 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 forever. Maybe. Do you guys know what we call numbers like pi and square root of 2?
Irrational?
Say again?
Is that irrational?
Irrational. I love it. It's crazy. We got all creative. These are rational. So anything that doesn't fall into this is irrational. It's like pi, square root of 2, so forth, right? What about square root of 4? Is that irrational? No, because square root of 4 is 2. So when I say square roots, I mean square roots that you can't do directly. The minute it's something I can't do the square root of, it's irrational. It's got no chance. Okay. So what we're trying to do is we've got now every piece of what we call real numbers. So we got real numbers. Then we got over here, we got rationals. And then we got integers. And then we got whole numbers. And then we got counting numbers. So counting is 1, 2, 3. Whole adds 0, which makes sense. They're the whole numbers, and 0 looks like a freaking hole. Integers adds the idea of negatives, right? Rationals adds the idea of fractions. And then real numbers adds the idea of irrationals. I like it. Okay, maybe. And of course, go ahead, say again.
Under whole numbers?
Counting. 1, 2, 3. And then whole numbers, we had to invent the idea of 0, that's whole numbers. And then we invented the idea of negatives, and then we invented the idea of fractions. And then eventually we invented the idea of freaky shit. Okay. So at some point in history, people thought this didn't exist. -3 was like insane. And then at some point in history, people thought square root of 2 didn't exist. And of course, now still people think that things like square root of -1 don't exist, but it does. Poor little thing. Okay. Maybe. So, just to kind of complete this, over here, we have what's unfortunately called imaginary. At some point in history, people want to call negative numbers imaginary. And then we kind of fought against that. And then they're like, and then this stuck. Anyway, enough about imaginary. So let's talk about, what I've introduced with this are weird-ass things like pi, that we're not going to necessarily talk about right now. But we also added the idea of roots. Square roots, what about cube roots? Cube roots, what about fifth roots? Fifth roots, what about 77th roots? 77th roots. All right. So let's talk about just those right now, how do roots work. Okay. So let me ask you what's going to be possibly a silly sounding question. What is the square root of 25? Why?
5 squared.
Because 5 squared is 25.
So another way to think of it is, and real quick, before we go any further, what's understood to be right here? A 2. I love it. Kick-ass. It's the most commonly used root, so we just decided not to write the 2 all the time because math people are lazy or frugal with your time. One of those. So this is true because it takes 2 5s to multiply to be 25. So, for example, if I try to do the square root of -16 just using real numbers, what's the square root of -16?
4.
What's 4 times 4? Don't bring those in, but you're right.
4 times 4 is 16.
Part of me loves that. The rest of me, we'll leave that out for now. So again, 4 times 4 is 16. So is the square root of -16 4? The 2 4s make 16?
Yes.
I mean, -16? The 2 4s make -16.
One
So,
negative and one.
No. What's this whole idea about? 2 of the same thing. The answer to a square root is the number it takes 2 of to make that number inside. It's impossible to have real numbers.
It'd be 4 and -4.
Are those the same number? No. So the answer to a square root is what it takes 2 of to make the inside.
And you can't do that.
Can't be 4 and can't be -4, because 2 4s make 16, 2 -4s make 16. Shit, right? So officially we would just say this is not real. But some of you guys know I love it. I'll put it on the side here. The answer is 4i. But again, don't worry about that. Okay. All right, what about this? What about the cube root of 27? So what are you thinking in your head?
Well, I was thinking 9. But that doesn't
Doesn't make sense, right? Because the general idea of a root is what does it take this many of to multiply to be this? It takes 3 9s to add to be 27.
Or I was thinking 3 cubed.
Sure. So what does it take 3 of to make 27 when you multiply? 3. Because 3 cubed is 27. Kick ass. Right? So what if I had to do something weird as this? What do you got, Jeff? Yeah, let's do 5th root of 243. Shit, Jeff, just raise it up, man. You go from frickin' cube root 27 to that. So, think about this. 27, isn't 27 9 times 3, which is 3 times 3 times 3. And then you can see that there are 3 3s. So there's a way to attack this. Can you start breaking down 243? What goes into 243?
9 and 27.
Okay?
And 27
Keep going.
And 27 is 9 and 3.
Did we just figure out 27 is 3 times 3 times 3?
Yes.
And what's 9?
3 and 3.
3 and
Do you see a group of 5 things?
Yes.
1, 2,
Yes.
3, 4, 5. Oh, yeah.
What do you see a group of 5 what's?
3 fifths.
That's the answer. What does it take 5 of to make 243? It takes 5 3s. That's why the answer is 3. So powers make things get bigger for the most part, most of the time. Radicals, roots, cuts them down. They are inverses of each other, right? If I say, write 3, and then I say, okay, do it to the 5th power, now you make it 5 3s. If I say 243, now do the 5th root of it, it cuts it back down to 3. It goes the other way. They undo each other. Okay, maybe they are opposite operations. What do you guys think about this? What about the 7th root of -1?
Oh. Now I'm lost in that one.
So what's the question you ask yourself? What does it take? What does it take?
7 of.
7 of
To get to negative.
to multiply to be -1.
It's -1.
-1, right?
Because odd numbers. An odd power.
Yeah, so if you have an odd number of negatives, can the answer be negative? Yes, the answer must be negative, correct? Yes? If I have an even number of negatives, real numbers, can the answer be negative? No, because pairs kill each other, right? So therefore, even roots cannot handle negative inputs. Because there's no freaking way to make that happen with real numbers. Odd roots, very laid back, whatever you got, man. Because if you have an odd number of negatives, 1 is left over. It can be odd. It must be odd. So we can do odd roots of negative numbers. We cannot do even roots of negative numbers and stay real. Gonna like it? No. All right. Some nifty shit here. All right. Let's do this. I'm going to let you in on a little secret. I kind of wish, it's going to be really weird for you, I kind of wish we had never come up with the radical notation. It is actually completely unnecessary. But we're all cool with it, right? We all know it, so why would I'm not going to get rid of it. It's sort of like trying to make America go to a metric system, but let's go back to a nice thing. Square root of 9.
That's 3.
Let's see if this, yeah, it's 3. Why is it 3? Because what do you get when you cut 9 in half multiplicatively? Holy shit. So when I cut 9 in half, listen. When I cut 9 in half additively, I get 4.5. Because it takes 4.5 and 4.5 to add to be 9. What do I get when I cut it in half multiplicatively? I get 3, yes? Because 3 times another 3 makes 9, correct? All right. So I say weird things like that. I'm cutting 9 in half multiplicatively, but now does that make sense? Because just saying cut in half is actually not good enough. We normally think that means additively, but it actually could mean multiplicatively. So what I'm trying to tell you is, another way to write this is 9 to the 1/2 power. What the shit? So, real quick. What is 1/2 of 4? Let me make this 8, sure. I want to be careful with 2 and 4 is weird. What's 1/2 of 8? 4. Why? Don't use the word divided by in your explanation. What's 1/2 of 8 is 4. Why?
Because 8.5 is 4.
4 plus 4 is 8.
Because 4 plus 4 is 8. What are coefficients? Again, what do coefficients mean? What's 2 times 8? 16. Definition of coefficient. What's the definition of multiplication? What's the most basic definition of multiplication? Repeated addition. Yes? So this means 2 8s make 16, right? And of course, half of an 8, so this is 4 because it actually takes 2 of these to make this. So you're thinking about, if I cut 8 into 2 equal parts, I get 4 because it takes 2 4s to make 8. So I'm sort of thinking backwards along the whole way, which leads to the idea of division. Now, square root of 9, if I instead looking at it like this means half of 9 multiplicatively, the same way this means half of 8 additively. Because what are coefficients based on? Addition. What are exponents based on? Multiplication. Yes? Maybe? Okay. So the same way that half of 8 is 4, cut it in half. Half of 9 this way is 3, cut it in half multiplicatively. So how would you rewrite the cube root of 27 with a fraction in it?
27 to the 1/3.
Yeah, 27 to the 1/3. Kick ass. So like I like to tell people, roots on most plants are where? Are they on the top or are they on the bottom? On the bottom. So when you rewrite roots, when you rewrite radicals, the root goes on the bottom. Same way as most plants. I love it. I said that a long time ago. I think my 3rd semester teaching, and the student in the back is like, I'm a botany major, and the tubers, the roots are on the top. I'm like, oh my God, okay. Most plants. It was just kind of, it was fantastic.
Are we gonna watch that video?
Maybe. I said I might. We'll see. We're almost, oh good, we're almost there. Sort of. Yes, we're almost there. So nothing we've done, I don't think anything we've done is too different. You guys have seen this stuff before, correct? Nothing too weird. They do shove a lot into this last section. They actually have some algebra stuff. And I do want to show you, let me just show you, let me do this. I'm going to show you 2 things. I'm going to show you some nifty manipulative stuff. I'm going to manipulate you. Alright, let's see what I got. Alright, I'm almost certain you guys have seen this kind of idea before.
Yeah, you add 5.
The idea of a balance for equations, where you explain why you do the same thing.
Not balance, but
You explain why you do the same thing to both sides algebraically in a very physical way, right? So the whole idea behind this kind of manipulative thing is you put, how many unknowns do I want on this side? I want 3 unknowns. You see how it's unbalanced now? Is that all I want on this side?
No. Wait.
A 1.
And a 1, right? 3 unknowns plus a 1. What do I want on this side?
A 4.
1, 2, 3, 4. Now it's balanced, right? Kind of like that. So the whole idea now is, it would be a lot easier if it was 3 of these equals a number, because then I could figure out what each one is very easily. Just divide, right? So what do I have to do so that it's not out of balance? What do I have to do to both sides? Take one away.
Oh.
So I'm going to subtract 1 from each side. And if I don't do it to both sides, of course, it's really simple to understand physically that it's going to be out of balance, which equates to the mathematical idea of you created an equation that's not equivalent to the one I was given originally if it's out of balance. So if I take 1 away from each side, go. And now, of course, what do I do to both sides?
Divide.
Yeah, I cut this in thirds, and then I'll know exactly what x is. Become a 3. Come back, look at us go. Yay. All right, so this whole idea of balance when you're teaching equations is a really nice thing. And of course, you could actually have a real scale in there and do some shit with that, depending on what you've got available when you get to wherever you're going to be. So the last thing I'll do, I'll go ahead and show you. Let's see. Here it is.
Primary care.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola.